Thank you again for joining our afternoon webinar of benefits of a simple year-round CRT solution. My name is David Hahn, and I am the Director of Marketing here at the Kavu Group. I will go over a few beginning housekeeping things, and then I'll turn it over to our Director of Thermal Engineering, Iftikhar Ahmed. So just to let you guys know, everyone has been muted upon entering the webinar. If you have any questions, there's a question and answer tab at the bottom of your screen that you can use. Questions will be answered at the end of the presentation. If you have any other comments or questions or things that you'd like to add, feel free to include those as well in the question and answer section. We will be checking those and handling it from that standpoint moving ahead. Again, like I said, my name is David Hahn. I'm the Director of Thermal Engineering here at the Kavu Group. Director of Product and Marketing here at the Kavu Group. Iftikhar Ahmed is our Director of Thermal Engineering, and he will be handling the majority of the presentation today. A little information about us. The Kavu Group has been involved in temperature management and control for over 40 years. We've got an almost 80,000 square foot building here in Dayton, Ohio. And we do have a global presence for manufacturing and distribution of our thermal management and thermal monitoring solutions. And a lot of our innovation for R&D and customization. You'll see our thirst for innovation and R&D specialty with some of the stuff that Iftikhar will be talking to you today. Essentially, our mission as an organization is to develop advanced thermal solutions for companies concerned about how temperature affects their product safety and integrity. So basically, we want to make sure that what you have is safe to your customers and is delivered within the temperature range that you require it to be. So without any more from me, I will turn over to Iftikhar, and he will talk through the rest of the presentation for you today. Again, as a reminder, if you have any questions, please fill out the question and answer tab at the bottom, and we will answer them at the end of the meeting.
Thank you, David. This is Iftikhar Ahmed. I'm the Director of Thermal Engineering at Kavu Group. And today, my presentation will be about a controlled room temperature shipping system for pharmaceuticals, which require temperature assurance over the transportation cycle. So in terms of CRT, controlled room temperature, right now, we don't have a very clear definition of what that means in terms of a specific temperature range, as opposed to, for example, when we talk about refrigerated temperature ranges, the most accepted and defined term is 2 degrees to 8 degrees centigrade. However, for control room temperature, the definitions can be quite varied. The USP definition is very narrow. It's between 20 degrees centigrade to 25 degrees centigrade. But depending on the product and the manufacturer, some of them can be as wide as 2 degrees, 30 degrees centigrade. So there is a fairly variable range. But the most common range so far is between 15 degrees and 25 degrees centigrade. So that's the area of focus in developing this packaging system. So in my presentation, I'll be talking about what are the important factors which are needed to develop such a shipping system, and how do we go about making it a simple and easy to use system for the user. Some of the factors that have to be kept in mind to develop such a system for CRT, obviously the product temperature range. So given that there's such a wide range, we have to, the design can change depending on what range you're designing for. Then also product stability criteria, allowable excursions play a part in it. If we have excursions which are allowed, then we can be more flexible with the design. However, if you have a strict temperature range, then the design has to be much more specific. Another factor is obviously the duration of shipment, whether you're designing for a domestic shipment, which is 24 to 48 hours, or for a more international shipment, which is, say, 5 to 7 days. So those are also considerations. Another important factor is what ambient profile the system is going to perform against. So typically we use ISTA standard profiles, and those are the profiles that have to be considered. Sometimes certain users would have their own shipping lane data that can be utilized as well. and designs can be made according to that. One of the misconceptions is that, people are used to having a refrigerated packaging system for refrigerated products 2 to 8C, and they think that they are able to use those packaging system for CRT as well. However, that's certainly not the case, and I'll explain that to you in a little bit. Now, why is this more of a focus on control room temperature shipping in the last, I would say, 10 to 12 years? And I wanted to show you some data from the FDA approval of new molecular entities for last year, for 2023. So last year, 55 new drugs were approved by the FDA. And as you can see, among the 55, the storage and transportation requirements for CRT are quite significant. Almost 30 out of these 55 drugs reference CRT range as a storage and transportation. So as you can see, more and more pharmaceuticals available in the market are operating in that control room temperature range. And I think the main reason is essentially convenience to the user. If you have a CRT product, it's easier to store at home and you don't require it to be refrigerated, where you can have all sorts of issues. If the refrigerator is not completely sealed or the temperature control is poor, you can lose efficacy of the product. So that is one of the main motivators of developing more and more CRT products. So hence, since you have a significant amount of CRT products being introduced into the market, the need for having a specific CRT transportation shipping solution is becoming much, much more urgent and is required. So let's look at, I had mentioned that refrigerated pack out. So you may already have a shipping system which is qualified for a refrigerated shipment, how it differs from a CRT shipping system. So let's look at some of the ambient profiles that are used to qualify these shipping systems. The most common one, which I'm sure a lot of you are familiar with, is the ISTA 70 profile. So the ISTA 70 summer profile is shown in the red solid line and the winter profile in the blue solid line. Now, the challenge in a shipping system is essentially the difference in temperature for the product at which the product has to be maintained and the ambient conditions. So if you look at the ISTA 70 profile, the summer profile, the maximum delta T from the upper limit for a CRT shipment and the temperature of the profile is about 10 degrees C. However, if you look at for a refrigerated shipment system, the maximum delta T from ambient is 27 degrees, so it's more than double. So the challenge for a CRT solution is not as much in the warm profile as is for a refrigerated one. Now that is completely opposite when it comes to the winter profiles. So if you look at the winter side, the delta T between the CRT lower limit, which is 15 C, and the ISTA 70 winter profile, which is -10, is 25 degrees. And for the refrigerated is the opposite, where the delta T is now 12 degrees. So the challenge for the CRT is more on the cold side to protect from the cold side, which is completely opposite to what you see in the refrigerated shipments. So what are the main challenges for CRT packaging at this time? One of the important things is that people want convenience. You want to have a shipping system which should be available for year-round shipments. You don't have to worry about changing the pack out, changing the PCMs, staging material or the gels, or the conditioning requirements, depending on the weather conditions. Now, that means that you would like to have a universal packaging system. However, for a standard ISTA profile, like ISTA 70 profile, which is a fairly challenging profile in terms of temperatures, developing a universal shipment for CRT is definitely a challenge. Then also, typical CRT packaging systems that are currently available would require, different, even if they use the same kind of gels, they would require different conditioning for summer and winter. So you want to make sure that, the gel is frozen in the summer so that, it can phase change with warm conditions. and you want to make sure the same gel is liquid in winter so that it starts freezing when it experiences cold temperature. So obviously there is some amount of temperature management that has to be done before the packaging system can be sent out. Also, there are the phase change materials or the gels that are used in these systems would require conditioning at particular temperatures which are not readily available, or we can use standard equipment for that. You may have to use specialized thermal chambers or incubators to condition those gels. Even if you use standard equipment like refrigerators and freezers, which operate at freezers typically operate around -18 to -20 degrees centigrade, and refrigerators around 5C. You can't use the gels as conditioned into the pack out straight away, because obviously those temperatures are out of the range of the product. So they have to have some kind of a warm up or bench time before pack out. Now that bench time can vary a lot depending on your environmental conditions, and there is always a possibility, risk of product getting out of criteria when they come into contact with such gels. Then another factor also is the cost. So there can be a significant variation in the cost of the system depending on your temperature range. If you have a very narrow temperature range, say 20 to 25, then you have to have very specific kinds of gels or phase change materials to maintain those temperatures, and that can increase the cost. But if you have a much wider range, say 2 to 30 degrees centigrade, then the amount of gel or the kind of gel that you use don't have to be as cost prohibitive. So given all these factors, we looked at trying to come up with a system which would be simple, which would require minimum amount of a changeover during the year as you are shipping throughout the year. And the product that we developed is essentially called Adaptec CRT 365. This is a universal design, which means you can ship it year round during winter and summer with the same amount of conditioning, with the same temperature conditioning, and the same components that are used year round. So you don't have to change over with the season, and the system can work as efficiently throughout the year. The system is designed to the most challenging industry standard, which is the ISTA 70 summer and winter profiles. This system is a single-use system, so it is qualified for 60+ hours of performance within a specific temperature range. The temperature range that it maintains for your products is the one I talked about, which is 15 degrees to 25 degrees centigrade. All components in the system are conditioned at 20 degrees centigrade. No specialized equipment required. You can condition at this temperature within a lab environment, and there is no bench time. So as the PCMs are conditioned, they can be packed straight into the shipper, and it is ready for shipment. So one of the key elements in developing such a system was to select the right kind of phase change material. And that is one of the developmental challenges that we had to work through to develop this system. And I'd like to go through some of the elements that were required to develop such phase change materials. Now, because we want to design a universal system, we want to make sure that it would be a combination of different types of PCMs, because there would be a phase change material which would work against protecting from warm temperatures and as well as from cold ambient conditions. And another challenge is to make sure that these PCMs have a phase change temperature range within the specified product temperature range. That is, they should phase between 15C and 25C. Another important factor is that we want to make sure that these PCM phase temperatures have minimum amount of variation around their phase point, which is very critical, because if you are operating within a range of 15 to 25C, you want to make sure that the PCMs phase within that range and do not vary a lot, because the chances of getting out of criteria can be high then. And this is again something which I'll explain in the next slide. For engineered PCMs, this is a challenge compared to, say, using something like water. Also, we wanted the PCMs to be conditioned at a common room temperature, So that was another challenge to make sure that you can condition them completely at a 20 degrees centigrade. And another important factor was that these PCMs should be able to undergo thermal cycling, which is basically a freeze-thaw cycle without significant change in their thermal properties. So that's another thing with engineered PCM is that as you go through multiple freeze-thaw cycles, its thermal properties may get degraded, and that was very important that we make sure that they remain stable. Another important factor is that the PCMs should be encapsulated in such a way that they should provide complete coverage of the product to prevent any temperature excursions within that product space. If some of you have ever done thermal testing, you would have noticed, especially with large product payloads, that you will have a significant temperature difference from the center of the product space to the corners. So the objective here was to make sure that the PCMs are applied in such a way that they provide as a large amount of surface coverage to the product as possible to prevent these temperature excursions. So I was talking about the variation in phase temperature. So I just wanted to give you an example of what are the challenges in doing that. So one of the PCMs that was developed was basically a warm PCM, which would protect against hot temperature conditions, ambient conditions. And this PCM would have to be conditioned in a fairly narrow range. So it has to be completely solid before being packed out. So if it was conditioned between a range of 20 degrees and 25 degrees. So the first PCM that we developed had a freeze temperature which was very close to 20 degrees centigrade. So you can see that one, which is in blue curve. So the conditioning at the temperature it freezes is closer to 20 degrees, which is the ambient condition. The delta T is small, which means it would take much longer for it to condition, and it may not completely freeze. So which means some portion of its latent energy would not be available for us to maintain product temperatures. So then we had to go and do a fine tuning of this PCM so that we could elevate its freeze temperature and which would allow it to condition completely at 20 degrees centigrade. And that's the PCM curve that's shown in orange. And that one has an elevated freeze temperature, which means it will condition more completely at 20 degrees centigrade, yet its temperature would be below the 25 limit. Another factor is also that when the PCM melts, it should melt more uniformly and not over a wide range of temperatures, because we want to make sure that the amount of latent energy while it's melting is available at the particular phase temperature that we want. This is a significant challenge for engineered PCMs as compared to water. Water has a very well-defined phase temperature, which is 0 degrees, and there is very little variation for water around that phase temperature. However, with engineered PCMs, you can have a delta T of as much as 1 to 1.5 degrees across their phase temperature. And that would mean that its phase change energy is being distributed over that temperature range. So again, as you can see, the PCM1 had a much wider range. That's why you don't see a very well-defined phase curve, whereas the orange, the sample 2, had a more defined thaw range, and it thawed within that temperature range of 20 to 25 degrees centigrade. The second point I'd mentioned was that we want to make sure that the PCM is stable over multiple freeze-thaw cycles. So that's another big challenge where we looked at one formulation, which is shown in blue, where we looked at the freeze point, and we saw that the freeze point of that particular PCM started deteriorating or started getting reduced over multiple freeze-thaw cycles. So after 15 cycles, it had gone down almost a degree, and it getting closer to the conditioning temperature of 20 C, which means that it will not completely condition at 20 C, or it will take much longer to do so. So then again, we had to fine tune this PCM, and the sample number 2 is the one where we were able to minimize this deterioration of the phase temperature over multiple freeze-thaw cycles, and it remained consistent after 15 cycles. Another property of PCMs, which is significant in terms of its performance, is thermal conductivity. So thermal conductivity essentially is a property of a material which determines the rate of heat transfer within that material. So when the thermal conductivity of a material can be quite different when it is in a solid state compared to a liquid state. So on the left side, you see a graph of the thermal conductivity of water when it is frozen and when it turns to liquid. So as you can see, frozen water has a higher thermal conductivity, somewhere around -20, it's somewhere around 2.5 watts per meter C. But as soon as it melts and becomes liquid, it drops quite dramatically to about 0.5 to 0.55. So what happens is that when you have a higher thermal conductivity within the PCM, the amount of heat transfer, the rate of heat transfer will be faster, which means that the PCM is going to phase much more quickly. Hence, the duration that you want for a PCM will be less. Engineered PCMs that we utilize in our CRT system generally will have a lower thermal conductivity. So as you can see on the right side, that's a graph for one of the CRT PCMs. So in a solid state, it has a thermal conductivity of around 0.25, which is an orders of magnitude less than what you have for solid water, which basically means that this PCM is going to phase at a slower rate compared to water, and hence will give us more duration. Now, that doesn't mean that the PCM will have a longer duration at a constant temperature, because there is another property which comes into play, which is the latent energy of the system. So what we are trying to do is reduce the thermal conductivity of the PCM to mitigate against the lower latent energy of PCMs compared to water. Another secondary factor, thermal property of PCMs, which is useful in maintaining temperatures, is the specific heat. The specific heat basically is the sensible heat gain for a material. So it is basically the amount of energy that is required to raise the temperature of a unit mass of material to a unit degree of temperature. Again, the specific heat value changes significantly from solid to liquid state. Now, water is unique in that sense that it has a much higher specific heat in its liquid state than most other materials. What that means is that once your gel or frozen PCM is completely phase changed into liquid, then there will be a rise in temperature as heat is absorbed. That rate of increase is determined by the specific heat. The larger the specific heat, the slower the rate of heat gain and temperature rise, which means you can gain some additional duration in the criteria, the temperature criteria. So water, there aren't many, unfortunately, phase change materials which can compete with water in terms of its liquid CP value. But again, developing a PCM, one of the things to keep in mind would be to try to increase the liquid CP value of these PCMs. Now, the most important thermal property of PCMs is essentially the latent energy. So the latent energy is essentially the energy that is required by unit mass of a PCM to completely change phase from solid to liquid or liquid to solid. And that is the property of phase change materials that are utilized in a shipping system to maintain temperatures. The latent heat energy of a unit mass is directly proportional to the duration you have to maintain a particular temperature, which is the phase temperature. There are different types of phase change materials. They're listed on the right side in the table. The most common is water, obviously. It has a phase temperature of 0. Latent energy is very high, one of the highest that are commonly available, 334 kilojoules per kilogram. However, the water's phase change temperature is not suitable for a CRT shipment. So it's very limited use in trying to do a CRT shipment. So if we go to a CRT PCM material like a PCM 18, which phases at 18 degrees centigrade, the latent energy for such system or such PCMs would be much lower. As you can see here, it's about 190, so it's about 40% less than water, which basically means that for the same amount of PCM, you will get less duration compared to water. or you will need more PCM in terms of mass than water to achieve the same duration. However, and some other factors play into it in how long you can maintain temperatures using a particular PCM. And one factor is actually the temperature difference from ambient conditions. So the graph on the top will show you the difference. So here in the blue line, the orange line represents water. We can show you the longest duration of water because of its latent energy. But if you look at the 18C PCM, that actually has a comparable, it is a little bit less than water, but still very comparable to water. And the reason is, even though it has less latent energy, the delta T from ambient is less because it is phasing at 18 degrees. So the delta T is less than what water would have, which is about 40 degrees, and 18C is about almost half. And that also is a factor in how PCMs behave in different temperature conditions. Another challenge which I had mentioned in our design of the CRT system was to provide as complete product surface coverage as possible. So I just wanted to give you some examples of what happens when you don't have adequate coverage of product with phase change materials. So on the top left side is an example of gels that are commonly used. These are polymer bags which are filled with liquid gels or liquid PCM. And when they are oriented in a vertical position, as you see there will be some amount of air gap. Because of gravity, the liquid is settled towards the bottom, and there will be air gaps on the top. And depending on the location of your temperature probes in your product space, you will see a temperature difference. And here we have two probes. One is in the center, that's TC1, and there's one on the top corner, which is TC2. So TC2 is more or less not covered by the PCM. So when you actually run a test, you will see there's a difference in temperatures between the two probes. And in this case, the difference is as much as 13 hours within criteria. Now, a better option would be to fill the PCMs in rigid bottles, and those are commonly used as well. They allow you to have a more complete or fuller PCM encapsulation. Again, but there will be certain amount of air gap because you can't fill bottles all the way to the top. And that will also have an effect. It is better than having gels, but again, you will see that there is a difference between the center probe and the corner probe of about 9 hours. So given these challenges, we looked into a unique, innovative approach on how we encapsulate PCMs. And that's where we developed this shape-stable PCM. So the shape-stable PCM basically is a phase change material which maintains the shape regardless of its physical state. So even in solid or liquid state, it will have the same shape. And it is basically a gel-like material with a higher viscosity. And because it is manufactured in a different way than just filling gels and bottles, we are able to minimize the amount of air pockets within the encapsulation. And here you can see a lot better coverage for the top and top corner in the middle probes. And now the temperature difference between the two has been reduced to 3 hours because of that. This shape-stable PCM, which is a proprietary technology of Carvu, was developed specifically for these type of applications. And it is something which you can develop at room temperature and with very minimum curing time. And another big advantage of using a shape-stable PCM is that it is almost leak-proof. So if you have a puncture or a leak at the seal in a liquid gel or a bottle, it will leak into your product space and spoil the product. But with this shape-stable material, even if there is a compromise of the external packaging, it will not leak out like the liquid PCMs. So once we have developed a appropriate PCMs for our CRT system, the next step was to actually design a complete system, including the insulation, the placement of the PCMs, the sizing of the PCMs, and then optimization of these properties to come up with the final product design. And one of the tools that we use very frequently and very effectively is thermal modeling. Thermal modeling tools are used to come up with an initial design, a conceptual design of the packaging system. And then the results obtained from it can be used to optimize various parameters. For example, if we have a variety of PCMs to use, we can try out different types of PCMs, optimizing their thermal properties to understand the effect on the overall thermal performance. And those properties, as I mentioned to you before, thermal conductivity, latent heat, phase change temperatures, all these can be optimized using this thermal modeling approach. Another factor we looked into was the actual insulation in the single-use Adaptec CRT 365 system uses expanded polystyrene EPS as its insulation material. And using thermal modeling, we can determine the dimensions and the thickness of the amount of insulation we need for the required durations. And as well as the PCM layout and the configuration, how we position the PCMs within the product space, also look at product coverage, what kind of temperature gradients we are getting in the product space, those can be determined as well. We can run this system in the software using multiple ambient profiles. So we can try out different types of profiles to see their performance based on that, and as well as figure out the temperature spread within the product space. Just a little bit about the thermal modeling process, how we go about developing a thermal model and what kind of results we get from it. The system is essentially developed as a 3D model in CAD, as you can see on the top left side. And then using that system, we develop what we call a numerical model or a finite element model from it. So the numerical model can be made more efficient based on the original CAD geometry. If the geometry is symmetrical, as you can see it is, we can reduce that model's size to a quarter symmetry, which allows us to save effort and time when developing the model as well as solving it. There are some additional tools within this software which allows us to simplify certain geometric details. For example, in the third image, you see that there is a EPS post in the corner, and that EPS post doesn't have to be specifically modeled in the simulation or the thermal modeling. We have tools which allows us to create thermal connections without actually having geometry. So we can create a connection between the PCM pouches, which are in red, to the walls of the EPS container without having any geometry in between. So once we have cleaned up the geometry and developed a numerical model or a finite element model, the next step is to define the initial and the boundary condition, the initial temperatures and the boundary conditions. So the system will have a certain initial temperatures at the start of the shipment, which basically means the PCMs have been conditioned at 20 degrees C, the product may be at 22 C, and then we apply a boundary condition. And the boundary condition is basically the environment, which is the ambient profile. In this case, the ISTA 70 profile is applied on the outer surfaces of the container. Then we set up the solver. Basically, the solver parameters are that we want to solve this system for 72 hours against this profile, and we want to obtain temperatures at regular intervals. In this case, we can specify anything from a few minutes to hours. And finally, once the system is solved, the temperatures are calculated over the entire geometry of the system. So everything, the insulation, the PCMs, as well as the product space, you can get a three-dimensional temperature map. And you can display it in a wide variety of ways. Some of the results that you get from the software allows you to get a very good physical insight into your system and allows you to optimize your system. The basic results or the primary results that you get are temperature distribution at each time interval. This is what we call a transient solution. So if you're running for 72 hours, you can recover temperatures at every hour, and then you can examine how the temperature changes over time. And you can plot them as graphs as well to look at the temperature performance at different locations within the product space. Another important consideration is the temperature gradient or the difference in temperature within the product space. So, the temperature can be different from what it is at the center of the product space to all the way to the corner, where usually the temperature will be a bit higher. So that can also be assessed. A data set of the temperature gradients can be plotted over the system to see where you have high gradients. For example, in this case, the blue shows like 0.06 to 0.1 degree centigrade difference within the product space, which is very good. But as you go towards insulation, you can see that there's a significant amount of temperature differences. Another useful tool, which is in simulation, is to look at the phase quality of PCMs. So the phase quality basically shows you the status of the PCM as it is melting from solid to liquid state or liquid to solid state. So in this animation, the blue sectors are essentially the warm PCM. That's the PCM that was frozen initially, and it shows how it starts melting as more and more heat is applied to it. And this is a valuable tool because this allows us to understand if we have overestimated the mass of PCM in the system or underestimated it. Because at the end of the simulation, if we see there is a significant amount of PCM which is still solid, that means our estimation of the mass is over, and we can optimize and reduce the mass of PCM in there. So I'd like to share, so we developed these CRT 365 system for two different payloads, 5-liter payload and a 10-liter payload. And then we did a triplicate qualification against the ISTA 70 profiles, and I wanted to share some results. So all that process of developing the phase change materials, their properties, and then developing the system and doing thermal modeling and optimization was done without creating a prototype. Once we had the final system optimized in our thermal software, that's when we went and actually developed the prototypes for the various components, put them together. We did some design testing first, and our design testing was minimized because of our approach with this type of optimization. And we were able to go to qualification very quickly. These are the results from the thermal qualification for the CRT 365 5-liter system. You can see for a maximum load on the summer side, we are getting about 69 hours, so 9 hours over our projected 60-hour qualification. And on the winter side, we are getting better results around 72 hours. And then we did the same thing for our 10-liter system. And this one is showing much better results. As you can see, it has more PCM in it. It's a bigger box. So this one is 85 hours for the summer side and 94 hours for the winter side. Our future development, which we are working on, is basically extending our CRT 365 design to develop a sustainable, reusable shipping system. And this will also be a longer duration shipping system, which would perform for a minimum of 96 hours and over. And what we're doing basically is utilizing the same internal components, the same payload size, the same phase change materials. All the components will be exactly the same, except the outer insulation will be different. Instead of using EPS, we'll be utilizing vacuum insulated panels, a higher R value insulation. So that will allow us to extend our duration to more than 96 hours. Again, the system will be designed for the same profiles, the ISTA 70 summer and winter profiles. We will utilize our shape stable PCM materials in the system as well. The shape stable allows the PCMs to be reused multiple times, which goes towards the goal of making this into a sustainable, reusable system. I'm sure some of you are familiar with vacuum insulated panels. They provide a much higher R value compared to other insulation materials, which basically means that you can use much thinner insulation. The dimensions of the insulation material will be much less than that of polystyrene, and that then implies that it will use less material, less weight, and less shipping costs. So some of the innovations that we are bringing to our reusable system is utilizing a different approach to VIP panels. Now, if you're familiar with VIP boxes, they usually consist of vacuum insulated panels, individual panels, 6 of them which are put together into a box format. Individually, VIPs have very high R value. However, once you put them together into a box format, the overall R value of the box will go down. And the reason is because of leaks. Because you are putting 6 panels together, there will always be some edge leaks along the edges where they come together, and that will bring down the R value. Typically, that R value comes down by 30 to 40%. So we wanted to address that, in that we have worked to develop this system where we will have these single panels which can be folded into A4 walls, so minimizing the amounts of edges that can leak. So overall, this box will have about half the edges of a typical VIP box. Hence, it will have a higher R value for the same size, which means we can go to a thinner wall than typical VIP boxes. Typical VIP boxes will use a 1-inch wall panel. In our case, it will be less than that, which means lower dimensional weight, lower transportation costs. We have done some preliminary testing of our VIP containers in the chamber, and these are some of the results. Again, using an ISTA 70 summer profile, as you can see on the top, that gives us about 115 hours of duration, so beyond the 96 limit. And then the winter is actually a lot better. However, this requires a certain amount of work. This was tested without an external shell. As you can see in the chamber, the box is there with some weights on the lid. And the reason is that external shell is essential for this type of VIP container, and the lid, the external lid, will push down the lid, the VIP lid, onto the walls and create a secure connection. And that is still work ongoing. And once that is done, the performance, as you see here, will be better than what we have tested so far. So I think that's the end of my presentation. I will then leave it up to you guys. If you have questions, I will be very happy to answer them.
Iftikhar, we did have a couple questions come in.
Okay.
The first question says, can you use water in combination with PCM in CRT packaging?
So the answer is qualified yes. Some people do use that, but I think the problem becomes is why do you use water is to basically condition the PCMs. So you can use a combination of water and PCMs where water can be frozen, or it can be at 5 degrees centigrade, and then it comes into contact with the PCM, which is at a room temperature range, and it conditions it. The problem with those things is that the water conditioning has to be changed for different seasons. So if you are shipping in the summer, the water can be cold, like at 5C, so that it conditions the PCM. But in winter, you can't use 5C because you don't want to freeze the PCM in the beginning. The PCM has to freeze while it is experiencing cold temperatures during transport. So the answer is yes, but you will still have to do a fair amount of temperature management and conditioning management.
And then one other question that came in is, what is the role of insulation in comparison with PCMs when you are making temperature controlled packaging?
So this is a question which I do get from some people, where they feel that they are able to use insulation alone to maintain temperatures, or just use some gel packs without too much insulation. For example, I've seen people use a corrugate box with a bunch of gels inside. Both components have an important part to play in maintaining temperatures in a temperature controlled system. The role of insulation is to reduce the rate of heat transfer from the external conditions, from the ambient conditions. But it cannot protect or maintain stable temperatures. It can just reduce the amount of heat coming in or leaving. Whereas the role of the PCM is to actually maintain temperatures at a stable level for a certain period of time. So if you remove insulation, the PCMs will maintain temperature, but the rate of heat transfer from the outside will be much increased. And therefore, the PCMs will phase very fast. and hence you won't be able to get the kind of duration that you need. And on the opposite side, if you don't use PCMs and just use insulation, there is no way to maintain temperatures, and whatever temperature you put the product in, it will start warming up, but the rate of warm up is not going to be as fast, but it will still keep on warming. I mean, so those are the basic differences.
Great. Thank you very much. I don't see that anything else has come in. If anyone does have any other questions, they can email me or email info@kavugroup.com. The email that came from me this morning with the login and link information is an email that you can reply to if there are any other questions or things that you have to do. Again, thank you very much for your time today. Iftikhar, thank you. It was very informative. And yes, if there's any packaging or specifically, obviously, CRT needs that anyone has, please reach out to us and we'd be happy to look forward to working with you. So at that point, we are done. So please have a great day. Thank you very much.
Thank you, everyone.